electron spin, you can use NV centers electron spin for probing, and nuclear spin for storage for quantum memory, and quantum states of atoms and ion also can be used because they are very sensitive to decoherence, and that's why they work. They are very fragile. That's why they act as sensors, very good sensors. Then nanomechanical oscillators can also be used for quantum sensing. So let's come to quantum communication, which has a lot of photonics, okay, into it, and the most popular application, as I told, quantum cryptography and quantum key distribution. Here one can have end-to-end communication, one node to another node, and one has quantum channel, classical channel, both are involved in quantum key distribution, and quantum repeaters and quantum memory are required if you want to have long distance quantum key distribution. And that's the problem, because we don't have quantum repeaters and quantum memory, and if you want to go for long distance quantum communication, you will have to use satellites. Without that, you can't, with present technology, you can't do long distance quantum key distribution. And another thing is quantum teleportation. So we have two entangled photons, okay, these are, suppose they are couple, and this fellow goes here and gets entangled with this, forms a couple. Now this fellow knows about this, okay, because they have formed a couple, they have become a couple, and this fellow, now this is disentangled, it has become disentangled, okay. So this fellow can pass on the information, and one can have some operation and can make the same state which is here. So that's how you do the teleportation. This is a photon, a quantum state which you want to transfer. You entangle these things, and then this information from here is passed through classical chain, is passed to this. You do the operation and you get the same photon as this. So that is quantum teleportation. So this is QKD system. Basically here you have to, when we say quantum key distribution, it's security of keys, that's what we are talking. So as our message is secure as long as our keys are secure, okay. So that's the idea of quantum key distribution. So we have to distribute our keys very secure, in a very secure manner, and for that we use quantum mechanical principles. So that's the quantum key distribution. We distribute keys, and then both parties are having same key, and then we encrypt the message using keys and decrypt the message using the key. And our keys are secure because we are using quantum mechanical principles. That's the basic point. So physical implementation, these are the equipments which you require for physical implementation. Coherent weak laser pulses are heralded single photons, entangled photons, as I talked about. There is not much time, I can't discuss in detail here. Of course, you need transmission channel, optical fiber or free space. So if you are going for satellite, you use free space, and otherwise fibers, these are photons you can transmit. Then you need single photon detectors or superconducting nanowire single photon detectors, or homodyne detectors and heterodyne detectors also, which is not listed here. So this is satellite. China is basically leader when it comes to satellite based quantum communication. All the quantum boom which you listen nowadays, it is because of this mission by China, okay, Messias mission. All the announcement from Europe, USA, everywhere, it's coming because of this experiment. They launched this satellite in 2016. By 2017 they have all the results from this and published in all very reputed journals. Okay, so they could show that you can have entanglement distribution for 1200 kilometers, you can have quantum key distribution across the continent. Okay, that's what they showed, and they have already a good number of ground stations where they could receive the quantum signal, and we are lagging here. India is lagging. We don't have a single ground station where we can receive the quantum signal from the satellite, and they have number of ground stations already. Already they have set up a quantum network in China using satellites. Okay. So since we were not having any optical ground station, so we submitted this proposal to DST, free space quantum communication, road to satellite quantum communication, so that we can have some ground station, portable ground station, which can be used for satellite as well as long distance free space quantum communication or quantum key distribution. Under that project we have good results. We have bright entangled photon source, we have like BBM92 entanglement based quantum key distribution, We have new QKD protocol, quantum key distribution protocol, and we have studied the security of the protocol, how the imperfections in your experimental setup can create insecurity to a quantum key distribution, that also we have studied. So, this is the entangled photon source, and this is the schematic which we have done this field thing, 200 meters thing, okay, it's 100 meters reflector. Okay. So, this is the technique you use for entangled photon, basically nonlinear crystal second order, you pump with laser, energy and momentum are conserved, you get signal and either 2 photons. So, single photon breaks into 2 photons, and that is how they are entangled, energy and momentum are conserved. So, this is basically entangled photon source, that is how this is the scheme which we have used, pump you see 405, and then it's it breaks into 2 photons 810, okay, degenerate we call. Then we measure the polarization here, you see, and we fix polarization of one and keep on rotating the other, and we check the polarization correlation. If polarizations are correlated, then they are entangled. That is how we measure the entanglement, and we observed that ours is highly entangled. You can see that Bell parameter, if it is more than 2, we have measured Bell parameter, it is more than 2, 2.63, much above the 2. So, ours is entangled photons in polarization. So, that is how you measure entanglement. Basically, these coincidences you measure. Coincidence detection is very important in quantum mechanics or quantum measurement. So, you measure the coincidences for different orientation of polarizer, and using these coincidences you find out the correlation coefficient, and then you plug in and you get the Bell parameter, and if it is more than 2, your photons are entangled. So, this is a quantum key distribution protocol using entangled photons. It is like you measure in random basis, okay, you choose random basis of polarization, both Ellis and Bob they are getting in photons, and they use basis selection randomly, and you assign bit values to these polarization states, and then you do the error correction and all those things, then you get the final. If you have selected the same basis, okay, if they have selected the same basis, you get the key, okay, you can notice here, okay, 110. So, that is what we have implemented in free space. You can see entangled photon source, it is going to one party, another is going to another, okay, Bob, 200 meters apart. So, that is what this is the field cabin where Ellis and Bob are sitting, it is being launched. This is entangled photon source sitting here. So, that is the arrangement you see here, Ellis, and this is reflected, this is Bob sitting. So, this is entangled photon source, one is going to Ellis, one is going to Bob, okay, just few minutes. So, that is how you measure the entanglement. After 200 meters we can see that we can measure the Bell parameter, it is more than 2. So, our photons are entangled, we have verified that. And then this is the technique, temporal filtering we call. So, we know that it is 200 meters apart. So, our second photons like which we are receiving at Bob end, that should be delayed by this. So, if you are sending S photon and we select this time window, okay, 648 nanosecond delay, then we get if you are sending H, we get high number of H polarized photons, and that will form the key. So, that is what, if we are sending, because we have generated HH plus VV, that is 2 minutes, HH plus VV, that is why if we say HH VV, so that will form the key. So, you just diagonal elements you sum up, you get the key, okay, and this is the error rate, and secure key rate we have this much. And we have studied atmospheric extinction coefficient, how that affects the secure key and key shifted key rate, that also we have studied. If extinction coefficient is very large, our key rate will be small. So, future is very bright, you can see that National Quantum Initiative Act of US, $1 billion National Quantum Program, UK, European Union Quantum Flagship, $1 billion, National Quantum Lab, China. China, you see the kind of investment, just one lab, $10 billion. They have also a national program also, just one lab they are investing this much. And then National Mission on Quantum Technology and Application, India, that is also good amount. So, what is the future? We are looking for fault tolerant quantum computing, scaling up and speed up with better fidelity for logic gates as well as qubits, for quantum logic and measurement of quantum bits, devices based on quantum sensing coming to market, advances in quantum computing to help further designing new devices, quantum network, quantum internet. Basically, we need quantum internet. Nowadays, we are so connected. Without quantum internet, there is no meaning of having quantum key distribution. Secure multi-party quantum computing. Once we have quantum internet, we can have multi-party quantum computing, globally linked quantum sensors and clocks also we can talk once we have quantum internet. And certainly we need new quantum algorithms. So this is the, we don't have any institute, like China is going to make investing $10 billion in one institute. We don't have any institute for quantum science technology. So next request, DST secretary sitting here, gone, but anyway defense people are sitting there. So we need really one institute for quantum science and technology, covering all the areas of quantum science and technology. This is the need of the country and time. So with that I say thanks. We don't have time, so questions can be asked later. Thank you. Sorry for taking more time.
Thank you. Thank you, Professor R.P. Singh. Good theoretical aspects and some practical demonstrations what you've done in your lab. I think we need to consolidate the effort. Just for information of the community here. DRDO 2 laboratories have demonstrated 10 kilometer QKD in Hyderabad and 100 kilometer between Prayagraj and Vindhyachal. So of course with some better rate and all that, Cuber and all that. So we need to consolidate that effort. I think we can do a wonderful job if we all come together and work together. The next talk is very, very important talk, and the speaker does not actually need any introduction to the community. Professor Shantanu Chaudhary, he is presently director of IIT Jodhpur, and originally he is from IIT Delhi. He is part of Department of Electrical Engineering. He holds BTech degree in Electronics and Communication Engineering and PhD from IIT Kharagpur. Professor Chaudhary joined as faculty member in the Department of Electrical Engineering at IIT Delhi in 1992. He was Dean of Undergraduate Studies and Director of CSIR's Siri Pilani during 2016 to 18. He is recipient of Distinguished Alumnus Award from IIT Kharagpur. He is a fellow of Indian National Academy of Engineers (INAE) and National Academy of Sciences (NAS). He is fellow of International Association of Pattern Recognition. He was awarded INSA Medal for Young Scientists in 1993, and he received ACCS CDEC Award for his research and contribution in 2012. A keen researcher and a thorough academic, Professor Chaudhary has about 300 publications in peer-reviewed journals and conference proceedings, 15 patents and 4 authored or edited books to his credit. So I invite Professor Chaudhary to come on the stage and deliver the talk on AI and cyber physical systems.
Thank you. Let me first thank DRDO and the organizers of Indian Science Congress for giving me this opportunity to talk to this audience on cyber physical systems and AI. This one? Yeah. So I think let me first introduce what is cyber physical system. I think this is something is in many cases is a mysterious phrase. So if you look at the cyber physical systems are physical, biological and engineering systems, and which are actually, if you look into it, has components and its operations are integrated, monitored or controlled by a computational core. Computers are networked and computing deeply embedded into every physical component. So if you look at the drone cluster which was being shown is an example of a cyber physical system. So in fact what we are talking about is not only applicable to physical systems but also even biological systems. any human, if we want to create a digital twin of a human being for health application, that itself will be a cyber physical system, and all of these components will be relevant in that context. So the computational core are embedded systems, expected real-time response, and most often it's distributed. Now obviously design and development of such a system is a challenge. And if you look into it, a simple idealized representation of system is like this. If you look at it, this is a physical plant. Physical plant is a physical system which is to be controlled. And this physical system has got physical interface. So whatever the sensing mechanism we are talking about, the sensors actually measure the condition of the plant, and that system can be even a biological system. So if there has to be a ICU and a patient is being monitored, then those parameters are also being measured by the sensors. Sensors do the local computation, and therefore it's a distributed architecture. So therefore there can be each element autonomous, but they are all connected over a distributed framework, connected over a network fabric, and that's how the whole system is being organized and managed. So this is what is today's architecture of any engineering system, which are providing you the lots of public utilities. In fact, your water distribution system, your power distribution system, even if you look into it, your transportation system are all examples of these kind of cyber physical systems. So these are examples that I have just picked up. If you look at automotive, manufacturing, avionics, energy, biomedical, military, and even buildings, smart buildings. So this is where the whole change of our physical engineering process is happening through this introduction of distributed networked control system. So if you see here, therefore, this is an interaction between cyber and physical. Computation, and computation is not static, it has to satisfy the temporal constraints, and in the temporal constraints, communication comes in as a player, which makes obviously the temporal parameters in many cases uncertain. And since it's an open system and connected system, the security and safety are of major concerns. So therefore, when we talk about such systems, so these managing these becomes really a critical point. So this is just summarizes what we discussed so far, and what we say that cyber physical systems are engineered systems that are built from and dependent upon the seamless integration of computation and physical components. So it's not just the computing, but also physical components which are involved into it. There are application domains: agriculture, aeronautics, building design, civil infrastructure, energy, environmental quality, healthcare, personalized medicine, manufacturing, and transportation. And in fact, in all of these, a major component comes in also as a security. And what we are working on, I don't have time to get into that in details, is the security of these cyber physical systems. And while this security, why this is a challenge? Because if we look at a transportation system, my transportation system, say railway network, can be any time attacked, it can be compromised, because it's completely on a communication channel. And how do you make sure that physical entities are secured despite these attacks? Similar, another problem that we are working on is also an attack on a cyber a drone cluster, and how do you secure such a drone cluster despite the disruption of the communication protocol. I shall talk about the AI interface and why it is required. This is an example of automotive CPS, because it's not just a car. When you're talking about a system, it is a connected car and connected transportation networks, and where 5G or any communication, mobile communication backend provides a support. And if we can develop the appropriate control system, we are talking about safer transportation, reduced emission, smart transportation, energy efficiency, even responding to climate change, and human-robo collaboration when you are talking about autonomous cars and semi-autonomous cars coexistence in the same system. So how do you develop such a system? Because we cannot understand how the AI comes in and how the secure issues or the safety issues come in unless we understand how these are designed and developed. The three basic steps involved are modeling, designing and analysis, and I have explicitly stated that modeling is what a system does. Design is a structured creation of the artifacts. It specifies how a system does and what it does. And analysis, the process of gaining deeper understanding of a system through dissection. It specifies why a system does what it does. Now, why this why comes in and analysis comes in is because in most of the cases we are considering physical systems. And it's not that for all physical systems you have the entire physics known beforehand, because the operation of a system is a function of various uncertainties involved in the world in which the system is operating. So, most of the valuable models that we talk about are that we use in a control system are deterministic. A model is deterministic if given the initial state and the inputs, model defines exactly the core behavior. But practical systems are non-deterministic because you do not know how different factors will perturb a system. And therefore we have to work with a non-deterministic framework, and the model in that case has to specify not a single behavior but a family of behaviors. And how you get those family of behaviors, it's a huge challenge of designing such a system. So therefore, what I say is that complex physical, biological and sociological systems, I shall come into it because the point which was being talked about in asymmetric warfare, that of information warfare, propaganda and generation of such information in a social system is also a function in a cyber physical world. So therefore, under such situations, deterministic models are impossible to have. So if you now go back and look into schematic of a simple CPS, I have a physical system and I have a computational platform, a network fabric, and this goes back and controls the physical plant. Now look at how the uncertainty comes in a very trivial way. I wanted to put it across to all of you. If you see, there is a network fabric, there are packet losses, there are unknown delays in the network, and there are uncontrollable scheduling, because I need to have a constraint scheduling to get the result, correct result in correct time for the physical system. And when we talk about a physical plant, there is a physical noise, there are parts failure of the plants, and there may be imperfect execution, and there could be unknown execution times also, because if I look at the computational platform, there are various parameters which influences your temporal behavior. So if you see these, all these are questions of uncertainty any physical system. When we talk about designing a controller of a system and design control engineering, even for a robo, we work with a variety of assumptions which are not always valid in a physical world. And that brings up a real challenge of designing these cyber physical systems. So therefore, handling uncertainty and indeterminism in CPS. Infeasible to model CPS for all possible situations within the environment, and there comes in what is called the data driven methods, because if the physics is unknown, I cannot write down the equation in a very simply put, and therefore I need to collect enough data from the world to augment the physics of the system so that I can handle uncertainty in a better fashion. And therefore we use now in a cyber physical system what we call learning enabled components. What are learning enabled components? If, for example, in a robo, I can incorporate object detection and tracking as a learned element for guiding the robo for a particular task. And since it's a component, I can replace the component and use it for another purpose, and therefore the overall design of the cyber physical system must ensure a reliable performance. So robo path planning in urban environments, attack detection in smart power grids. That's one of the problems that we said that is very, very important and critical to look at if we look at these current threats that we face. And also there are examples. So these are components. Another way you bring in actually the data driven models to actually handle uncertainty is also an end-to-end simple learning model, a convolutional network to map images from a front-facing camera directly to steering commands for an autonomous vehicle, which is very common example. I think we had also had such demos in the labs, and I think defense has worked on a number of such examples and demonstrations. This is a straightforward learning based control system, but where the components are not there. So here the model therefore comes down to this, is that this is a classical control. If you see the traditional CPS is a classical control design that we talk about. But here now what we are talking about, the AI software is taking the role of a controller. And it is therefore, if there is an input signal, AI is actually generating the control signal, which is activating the actuator and influencing the plant to change. I am not getting into details because if I take up an actual system, it will be too complex to cover in the short time. And therefore, the performance is measured by the sensor which goes into AI software as a controller. But now the question comes is, how do you design such an AI controller? So this is called a development workflow. And development workflow, I have used two examples. One is supervised learning, another is reinforcement learning. If you look at these, so there has to be supervised learning has to precede a data collection. But then data collection is a challenge because data collection also would require labeled data for the purpose of supervised learning. And when it's a cyber physical systems, and we are talking about there are so many uncertainties which can crop up, I cannot have a supervised labeled learning. And this is a very fundamental drawback of using classical machine learning, supervised learning techniques in the context of cyber physical systems. So therefore, although there has been examples and people have tried to, in fact have published some of the benchmark data to try out this kind of a controller designs. So assurance monitor training, by that you actually, so there is another very important point is to be noted here is that assurance monitoring. It is not just accuracy in terms of performance of a machine learning. That is, if a classifier classifies input with a certain label, it's just classification, but there is no assurance involved. That means I do not know when it is really failing. And that's any classifier, even if you have trained, it will accurate up to 99%. That means if I use in 1 lakh, then 1% failure is large. And the assurance is something very, very important. If I'm talking about cyber physical system for a practical application, let's say a power supply, we cannot actually expect 1% failure even in a power supply. So now the integrated system testing is another issue, data collection, performance evaluation. But what is important is that I do not have labeled data. See, if I don't have a labeled data, then what we are talking about is reinforcement learning. And reinforcement learning is essentially the reward penalty thing, and where we really do not put in the labeled data for the purpose of for the training. And so therefore, now with the deep learning, current trend and what we have done some experiments with are the deep reinforcement learning for training such systems. So DRL follows, I'm just giving a story kind of a description of the thing. DRL follows typical trial and error paradigm, learning the best strategy via repeated interactions with the external environment. And DRL requires to train an agent in an environment so that agent learns a best policy that maximizes the cumulative return. And at each step, agent has a state given by the environment and the agent itself, and it is required to take an action to transit from the current state to the new one, and what is the return for the new one. And this whole thing happens with reference to a simulator. So therefore, it is, if you look at reinforcement learning, a very simple example is a kid, when it looks at a candle, if it touches the candle flame once, he will not touch again. Because the pain is actually the signal which tells you not to do that. So therefore, the reinforcement learning is essentially the learning to figure out that if I take an action, what is the return that it goes into it. And a policy is a function that maps a state action to a real valued reward, and that's how the whole thing works out in terms of real life system. And today DRLs, that is deep reinforcement learning, is something very, very important and useful technique to look at for a number of these kinds of application scenarios. But that's not the end of the stuff, because then the CPS, it's just not a learning, and the accuracy of the classification is what is important. What is very critical, the CPSs are commonly used in mission critical applications which demand high reliability and strong assurance for safety. So assurance essentially is, what is important is that test data alone is generally insufficient for assurance of safety critical systems, because the point I am telling is that 99% working means 1% failure, so it cannot be used in that ways. So, so testing is used as a primary evidence, but what is important is formal verification of learning enabled systems are an active area of research, although it has not been explored to a great extent by machine learning. That's what is required today, and that's what is linked with what is called dependable AI requirements in these days. The temporal consistency is something also very important. So when we talk about machine learning, we do not talk about the deadline based performance of a machine learning systems. But when we are looking at in the context of cyber physical systems, it's very important to have the entire temporal constraint specified, and these temporal logic, that STL, is a standard language today is being used for specifying the temporal constraint for these cyber physical systems, because now your ML system has to be verified with respect to the temporal constraints in terms of its behavior. So if you see this unmanned underwater vehicle training, so it's an example. The controller is built on ROS middleware, and we have using simulator for the data, and this is a kind of a virtual configuration of the system that we considered. With reference to that, if you see that the neural network is a reference, and there is a testing data, and the problems there with certain assumptions, and there are goal control logic. Controller commands prevent collision with the pipe, because the scenario you have considered is that this UAV is actually monitoring a pipeline, underwater pipeline. And if the goal is to avoid collision with the pipe while maintaining the vision of the pipe, and this whole controller has to understand, and therefore if you see the whole work has been divided into number of goals, and with reference to the goals, the DRL is supposed to learn how this whole the monitoring control strategy to be built and incorporated. So now the other interesting point comes in, that when human cyber physical system comes in, because that's the robotic teleoperation. An example here is a forest fire. You'd like to control, if you want to control the forest fire, you have to have the human in the operator. Even in avionics and everywhere, there is a legal, ethical and political concerns for the human being. But now when actually human intervenes, that any intervention alters a sensorimotor loop that we have already designed. Now therefore the challenge over here is, actually if you go back, I think missed. So if you go back, that sensorimotor challenge, actually the moment you do not have a completely knowledge of the predictive control loop, the sensorimotor challenge actually can disrupt the system. Now that's again a challenge in terms of AI, when you really want to put a human in the loop for controlling such systems. And here I am showing that, as was being talked about in terms of asymmetric warfare, and where the cyberspace and the social space comes together, is a scenario where I have the socio-space interactions, cyberspace, and all of these comes together into what is called socio-cyber physical space. And if you look at in the socio-cyber physical space, the semantic linking cyber physical social systems becomes extremely critical. And today when you talk about deep learning, there are open areas, because we are not looking into reasoning in a very strong way. So semantic indicators and rules to link object across spaces, cyberspace to social space to digital space, and that requires relational reasoning, analogical reasoning, inductive reasoning and complex reasoning. And in fact, there are lots of work is now getting done in this space when you try to look at cyber social physical systems. Because social network and controlling social network, in fact, there has been examples where this kind of a CPS system has been used to identify the locations of earthquake on the basis of the local signals being generated, and where this reasoning is being used to modeling the systems and getting the decisions with reference to them. So therefore, to conclude, the data driven models, what I have just given a touch overview on, is data driven models enable CPS development for complex problems. And in fact, many of these problems that we talk about in a strategic warfare, internal security, controlling of robots, controlling of actually transportation networks, all belong to this category, and data-driven models are extremely important and critical in terms of having robust systems to be built. So reasoning models for situating CPS in social systems I've already talked about. These reasoning models are now today, it's not at the core of the attention. So those who are looking for new research areas and research problems, there's something to look at. And AI-enabled CPS components introduce new challenges: safety, robustness, dependability of AI, and temporal constraints for AI. And these are actually the
So, the last talk of this session is by Professor Rohan Paul on cognitive technologies. You would have seen there is a thread running among all the topics that we are talking of, and probably we'll talk more about this thread in the concluding question answer session. So in the interest of time, I request Professor Paul to make the presentation. Let me just read out his brief biodata. He is assistant professor in Department of Computer Science and Engineering with joint appointment in the School of AI at the IIT Delhi. His research program is aimed towards capable service robots that can perform complex tasks alongside humans. His research has received research grants from DRDO, DST and ICMR. Prior to joining IIT Delhi, he has served as postdoctoral associate at the Computer Science and AI Laboratory at MIT, working with Professor Nicholas Roy. He has also worked in Oxford University, BTech and MTech from IIT Delhi. Number of awards that he has received, I think very large number of awards, very celebrated researcher. So I'm, in the interest of time, I'm just shortcutting that and request you to make the presentation.
स्लाइड चेंजिंग का तो यहीं से है ना लगाएंगे इधर आ रहा है चेंज कहाँ से करना चेंज यहीं से करना ना Okay, good afternoon. Thank you for the opportunity to be here. I'm very grateful to DRDO for organizing this session. Among very eminent speakers, Professor Chaudhary just spoke. He's been like my teacher when I was an undergraduate at IIT Delhi. I'm really honored to be standing in front of him and this distinguished audience at ISA. So I think I'm the last speaker between the audience and lunch, so I will keep the discussion very, very small. One of the advantages of being the last speaker is I can reference back to all the wonderful ideas and the foundation that has already been laid by the talks that came before. So I'll keep the discussion short and focus on the cognitive element. And we've seen a number of presentations today that talk about autonomous systems, talk about cyber-physical systems and the various challenges. And the one that I'm going to pick up is going to focus more around, I would